Okay, so we'll talk about how we understand research results regarding statistical inference. So this is inferential statistics. All right, so samples and populations. So we rarely study entire populations, so our findings are going to be based on sample data. So again, if your population is 1,000 people, you probably are not, well, you may not be able to study all of them, so maybe you study 100 of them. So that's going to be the difference between a sample and a population. And we use inferential statistics to determine whether the results match what would happen if the experiments were repeatedly conducted with multiple samples, um, and which is going to enhance generalizability. And they help answer whether it can be inferred that the difference in the sample means reflect the difference in what we would expect in the population as well. So an example is in an experiment examining aggression in children who observe an aggression model versus those who do not, as we talked about. All right. And again, you can see here in regard to variance standard deviation. Again, your sample size, which is 10, and then the mean. You can see those who had a model of hitting that Bobo doll had a higher level of aggression than those who did not. And the standard deviation was about, 1 standard deviation from the mean in comparison to 1.2. And the variance, or again, the differences are going to be 1.29 to 1.43. Again, so this is just a basic info or data related to those groups in that hypothetical study. Okay, so inferential statistics. The equivalence of groups is going to be achieved by experimentally controlling for other variables, or if we have high levels of randomization. So we assume that if the groups are equivalent, any sort of differences in the dependent variable must be due to the presence of the independent variable. So the independent variable causes an effect in the dependent variable. But the difference between any two groups will almost never be zero. So there's going to be some differences in the sample in the control and experimental group. If you're doing an experiment, there will be some sort of difference. So inferential statistics are going to allow us to make assumptions about the true difference in population on the basis of sample data. It's going to give the probability that the difference between mean reflects random error rather than a real difference. So it's something else going on and not a difference between the sample and population. All right, then we have null and research hypotheses. So the null hypothesis is that the population means are equal and that the observed difference is due to random error. So as an example of this, you might, again, have a research study based on just world beliefs and their correlation with belief in conspiracy theories. So for a null hypothesis, you would say there is no predictive value of just world beliefs on conspiracy theory beliefs. Or there is no relationship between just world beliefs and conspiracy beliefs. Whereas the research hypothesis is that the population means are, in fact, not equal. So this indicates that the independent variable did have an effect. So in the case of the example I just gave, that just world beliefs do have a predictive impact on conspiracy theory beliefs. There is a difference. And we determine statistical significance. That's going to indicate if there's a low probability the difference between the obtained sample means was due to random error. So how significant are the findings in regard to the differences between the independent variable and dependent? Now, probability is the likelihood of the occurrence of some event or outcome. Now, in statistical inference, again, our assumptions, we want to specify the probability that an event will occur if there's no difference in the population. So maybe there's a hypothetical ESP experiment. We also have an alpha level. That's the probability required for significance. It might be 0.01 or 0.05. We're just going to use 0.05 in this class. We then have sampling distributions. This is based on the assumptions that the null hypothesis is true. And the sample size, the total number of observations, has an impact on determinations of statistical significance. And again, the more people that you sample, the more confidence you could have in your results. So This is the exact probability of each possible outcome of the ESP experience. Uh-oh. Hopefully you could still, yep, screen sharing. Make sure everything's on there. With 10 trials. All right. So again, in regard to, again, the number of correct answers, probability is next to zero. Again, probability of, again, correct answers being zero, there's a much higher probability than zero. But again, your highest is going to be right around two. People can guess pretty well. Now, group differences. We have T and F tests. What you're going to do for a statistical test, you have to have a null hypothesis, research hypothesis, and then, again, the alpha level, 0.05. Now, the t-test is commonly used to examine whether two groups are significantly different from one another. The t-test is a ratio of two aspects of groups. You don't need to know these formulas. JASP would run it for you, but a t-test is, okay, the group difference divided by the within group variability. And this is the formula associated with it. But it's really to examine whether the groups are significantly different. So these are the sampling distributions of t values, again, with 18 degrees of freedom. And again, you can kind of see, again, what the standard deviations are. And you can see what's in you can see the critical value here as well. And the alpha level, there's alpha level of 0.025 and an alpha level of 0.05 here. Now, and again, that's something that can be run in JASP and then interpreted. Now, degrees of freedom, DF italicized, this is going to represent the number of scores free to vary once the means are known. It's somewhat different. Critical values of a t-test are used depending on whether the test is one or two-tailed. This is going to be a two-tailed test up here. This is going to be a one-tailed. A one-tailed test, you're looking, the research hypothesis specifies a direction of difference between groups. The two-tailed does not specify a predicted direction of difference. Now, you also have the F-test. It's a more general statistical procedure than the t-test. And when a study only has one independent variable with two groups, F and T are basically identical in how they're going to run. The analysis of variance is also used when there are more than two levels of an independent variable. Again, maybe you have a placebo and a antidepressant, and when a factorial design with two or more independent variables has been used. Again, this can be run in JASP. Now, the F-test statistic is a ratio of two types of variance, systematic and error. This is going to, systematics, the deviation of the group means from the overall mean or mean score of all individuals and groups. So how much does that deviate? The error variance, this is how much deviation there is in individual scores in each group from their respective group means. So how much do individuals vary from the overall mean of that group? Now, the larger the F ratio is, the more likely it is that the results are significant. So that's what we're looking, that's the basis here. The larger the F value, the more likely it is that the results of your research are significant. That's the important thing here. And again, okay, so calculating an estimate of effect size, you can see that here. That's, again, that lowercase r italicized. You can also calculate Cohen's d. This would be another option in JASP. When comparing two means, again, which expresses effect size in terms of standard deviation units, that can also be run in JASP. And again, we talked about effect size. So again, we just use the R. Small is 0.1, moderate 0.3, large 0.5. If you're doing Cohen's d, though, in regard to running effect size, 0.2 would be small, 0.5 would be moderate, 0.8 would be large. We then have confidence intervals. This is going to be an interval of values within which there's a given level of confidence where the population value lies. It's represented in bar graphs as a vertical I-shaped line bounded by upper and lower limits. Again, the hypothetical aggressions experiment. And that, again, with confidence intervals here, you can see from 4 to 6, 2 to 4. The mean aggression scores from the hypothetical modeling experiment include the 95% confidence intervals that you can see here. All right, so statistical significance. Again, we've kind of talked about this, but the goal is to help us decide if the obtained results are reliable. And the significance level that we choose indicates how confident you wish to be when making the decision as to whether the results that you find are statistically significant. It's more likely also, again, when you have a large sample size. Now, there are type 1 and type 2 errors that might come into play and affect your overall results. So if you make the decision to reject the null hypothesis, or the decision to reject the null hypothesis is based on probabilities rather than certainties, the decision might not be correct. And so we might reject the null hypothesis and, in fact, say there is a significant relationship between just world beliefs and conspiratorial thinking. The errors may result from the use of inferential statistics. And that is if you reject the null hypothesis when, in fact, you should not reject it. Using a decision matrix, there are two possible decisions and two possible truths about the population, possible decisions. You can reject the null hypothesis or accept it. The possible truths, on the other hand, the null hypothesis is true or it is false. So, okay, again, this is the true side, this is the decision side. And again, if the null hypothesis is true, but we reject it nonetheless, that is going to be a type 1 error. Null hypothesis is true, and we accept the null hypothesis. That's going to be the correct decision. But if the null hypothesis is false, again, we say there is a significant relationship, in fact, and we reject the null hypothesis. That is, again, correct. Whereas if the null hypothesis is actually, again, it's false, and there is a relationship, but at the same time, we decide like, no, there is no significant difference. That's actually a type 2 error. So you have two different types of error here. Now, correct decisions. They occur in two situations. When we reject the null hypothesis and the research hypothesis is true, and when we accept the null hypothesis and the null hypothesis is true. Okay, those are going to be two correct decisions that can be made based upon the data. Again, a type 1 error is when we reject the null hypothesis, but it's actually true. The probability of making this type 1 error is based on the choice of significance or alpha level. So again, if you have a 0.01 significance level, it's going to be much less likely you have a type 1 error in comparison to if you have a 0.05 significance or confidence interval. The higher the significance or alpha level, the greater the probability of a type 1 error. Again, because there is that gap there that you are pretty sure you're correct, but not 100%. Type 2 error occurs when the null hypothesis is accepted, but the research hypothesis is actually true. The population means are not equal, but the results of the experiment don't lead to a decision to reject the null hypothesis, even though you should. So the probability of this type of error, it's related to three factors: that alpha level, again, the sample size, which might be too small, and the effect size, which also might be small. And again, decision matrix for a jury, okay? Somebody's innocent, but again, we find them guilty. That could be a type 1. Again, somebody's actually guilty, but we find them innocent. That would be type 2. Now, in choosing that significance level, you traditionally use a 0.05 or 0.01 as to the significance level and the decision to reject the null hypothesis. It also specifies how probable it is that there's going to be a type 1 error if the null hypothesis is rejected. And the significance level chosen and the consequences of a type 1 or type 2 error are determined by the use of the results. But nonetheless, these are the two significance levels that are commonly used. Now, interpreting non-significant results. The results of a single study might be non-significant even if there's a relationship between the variables, and it actually exists. But a meaningful result is more likely to be overlooked when the significance level is very low. Sample sizes should be large enough to find a real effect. So again, you want a so you might want like a 0.05 significance level. So there's a little bit of wiggle room. And then also you want a large sample size. And so you need a large sample size to rule out the possibility the sample is too small. And evidence that the variables are not related should come from multiple studies. Again, that replication as well to find corroborating evidence of your results. Now, the power of a statistical test determines the optimal sample size based on the probability of correctly rejecting the null hypothesis. There are programs out there that can actually determine what, based upon your study that you're conducting, how many participants should you actually have? And so they'll give you the minimum number, and that's going to give you a significant amount of power regarding the results of your study. And if you include more participants than that, that would increase your power even more. So, and there we go, power equals 1 minus, again, that type 2 error. The effect sizes and the desired power, the smaller effect sizes are going to require larger samples to be significant. At the 0.05 level, you're going to need larger samples. A higher desired power demands a greater sample size. Yes, and so you can't have too many participants. Researchers usually use a power between 0.7 and 0.9 to determine the sample size. That's what for mine I did. So I used a 0.05 level power of, I think it was 0.7 or 0.8 possibly. And the requirement for my sample was right around 110 participants, but I will be using 130 to ensure that there is enough power to come to an appropriate conclusion. So this is the total sample size needed to detect a significant difference for a t-test. Okay, you have the effect size, okay, 0.1, power of 0.8, and power of 0.9. So for effect size, again, of 0.1, again, which is very, very low. Power of 0.8, you need about 790 participants. Power of 0.9, over 1,000. So again, for mine in general, looking for a moderate effect size. Again, I believe it was somewhere in this realm, but nonetheless, right around here, to have about 100 participants in general. But to ensure high enough power, I'm vying for more. But again, to have that higher effect size. Okay. Importance of replications, as we've talked about, we really don't attach a lot of importance to the results of one study. In order to study any phenomena, we're going to have to study it intensively over many, many studies or many, many years. And so instead of inferring population values on the basis of a single investigation, we can look at the results of several studies that replicate previous investigations, also known as a meta-analyses. Now, the Pearson R, which we've already talked about, it's used to describe the strength of the relationship between two variables when both have interval or ratio properties, which we've talked about in the last chapter, and we will run. There remains the issue of whether the correlation is statistically significant. And so a statistical significance test can help to decide, okay, do we reject or accept the null hypothesis? And can we conclude that the true population correlation is in fact greater than 0? Now, there are statistical analysis software. These are some of them. It's carried out via specially designed, statistical software. SPSS used to be the most popular one. There's SAS, Systat, R, which a lot of institutions use. We will use JASP. And with your data, you will initially basically collect it and record it in a Microsoft Excel spreadsheet, and then it will be transferred over into JASP for analysis. And steps in doing the analysis, you input your data into Excel, you upload it into JASP, data are entered into columns. Yeah, it's easier to think of data as a matrix with rows and columns. Then we will give instructions for the statistical analysis, and you will then interpret the output, which we will do together. Here's some of the input and output. This is what your Excel sheet would look like. And this is, for example, the information that would be kicked out from JASP. Now, selecting the appropriate significance test. The variables we study might have to be nominal, ordinal, interval, or ratio scale. You might use nominal, ordinal, or interval, probably not using ratio in this class. A number of online guides and tutorials can help with which tests do I choose. The nominal scale properties have two or more discrete values, again, like male or female, interval or ratio. They might have many values, again, reaction time, rating scales. These are going to be called continuous variables in comparison to discrete variables, which are nominal in nature. All right, so research studying two variables. So studies whether the research studies whether two variables are related. First is referred to as the independent variable or predictor variable. Second is the dependent or outcome variable. It's also possible to refer to the variables as X and Y or A and B. You can use independent or dependent or predictor and outcome. So these are the statistical tests for different combinations of independent and dependent variable studies. So let's say, again, both of your variables are nominal in nature. You'd use a chi-square. If you have, let's say, again, does right-handed or left-handedness impact grade point average? Again, you have nominal. You have two different groups here for nominal. And then you have an interval or ratio. It would be a t-test. Nominal with three groups. Study time, low, medium, or high. Then an interval or ratio scale. It would be an ANOVA. Then let's say in general, you're probably going to have, this, the t-test, or if your independent and dependent variables are both interval in nature, like an optimism score, and how many sick days there were last year, you're going to use a Pearson correlation. And again, we'll walk you through that. Now, if you have multiple independent variables, some of the following situations represent more complex research designs. If you have two or more independent variables that are studied with a single outcome or dependent variable, again, an example of that could be what is the predictive nature of just world beliefs and education level on conspiracy theory beliefs? And so if that is the case, if you are going like, okay, you've got two independent variables and one dependent variable. In general, you probably don't have two nominal and then an interval or ratio outcome variable. But if you did, you would use a factorial design, or ANOVA. In most cases, you're probably going to have this situation in that you have, again, two interval or ratio scales. And so there's two or more variables here. And then an interval or ratio scale, you'd run a multiple regression. So with that being said, hopefully that just gives you an overview of the statistical analysis and inferential statistics. But again, I'm happy to walk you through this, help you out with JASP. Let me know how you're doing. If you have any questions and concerns, let me know. Otherwise, I hope you have a great day.